Good day, everyone. This is Chris with the Ancient Scholar, and today I'm going to do a quick review for my students for their respiratory physics course. This is going to be exam 2, and specifically I'm going to be reviewing the critical formula that will be negotiated on exam 2. So without further ado, let's get right into it. Okay, the first formula you need to be familiar with is the PaO2. This is the alveolar air equation. The PA, big A, of course, always means alveoli, and this is to calculate the pressure of oxygen within the alveoli. PaO2, big AO2 equals the atmospheric pressure minus the vapor pressure multiplied by the FiO2. Whatever that value is, you need to take away the PaCO2. This is the little a, so this is the arterial pressure of carbon dioxide multiplied by 1.25. In most cases, atmospheric pressure will be 760 millimeters of mercury unless it is stated otherwise. You can just assume that for most problems we're dealing with 1 atmospheric pressure. The vapor pressure is almost always going to be 47 millimeters of mercury. That is the water vapor pressure at 37 degrees Celsius. And when we multiply that value, atmospheric subtract vapor pressure by FiO2, remember the FiO2 needs to be in a fraction. So you would multiply 50% by 0.5. So make sure that you do convert FiO2 into a fraction, or you can easily get this calculation wrong. Okay, the next calculation is the big A minus little AO2, or this is known as the A to A gradient. You simply take the big AO2, the alveolar air, or the alveolar partial pressure, and you subtract the P little AO2 from that. So you subtract the arterial pressure of oxygen from the alveolar pressure. So you'll need to get the arterial, the P little AO2 off the arterial blood gas. The normal A to A gradient is 5 to 10 millimeters of mercury, so there's not a huge difference between the two. And greater than 10 typically will indicate some sort of a shunting or significant ventilation perfusion VQ mismatching occurring. Okay, the next calculation I want to talk about is the C little AO2. This is the content of arterial oxygen. Okay, the C little AO2 is calculated the following. We take the hemoglobin in grams per deciliter. We multiply that by 1.34 and then multiply that by the SaO2, or the saturation of oxygen. The SaO2 is obtained from the arterial blood gas. This is not the SpO2. SpO2 is pulse oximetry saturation. We actually need the SaO2, the saturation of hemoglobin from the arterial blood gas. And then you add to that value the P little AO2, the partial pressure of oxygen in the artery, multiplied by its constant 0.003. You know that 1.34 is a coefficient because we assume that every gram of fully saturated hemoglobin will carry 1.34 milliliters of oxygen, and we know that 0.003 is a coefficient because every millimeter of mercury of partial pressure of oxygen in the arteries will equate to about 0.003 milliliters per 100 milliliters of dissolved oxygen. Obviously, lots of things can change those coefficients, but those are the assumptions that we'll be running on in this physics course. The normal value for the CaO2 is 17 to 21 vol percent. Vol percent just means milliliters of oxygen per 100 milliliters of blood. That's just a way we typically write that in vol percent. Less than 17 generally indicates some sort of hypoxemia and possible hypoxia occurring. The next calculation that we want to look at is the VDVT, and I can see right now we had a nice little error. For some reason, Apple cannot get the iPad and their various computers, the MacBooks, to communicate effectively Therefore, if I do a keynote presentation on the iPad, apparently I can't get that presentation to look like it did on the iPad, look the same on my MacBook. It's a continuing point of frustration, and they've had years to figure this out. Apparently they can make Retina displays, but they can't make the conversion between devices seamless. Anyway, let's go ahead and get into the VDVT. VDVT is the dead space to tidal volume, and I remember this one by Paco minus Paco over Paco. So if you look at the formula there, you should have P little a CO2 subtract P ET CO2, which is not on the screen as I can see, divided by PA CO2. So that's Paco minus Paco divided by Paco. The PET CO2 is the exhaled carbon dioxide, so you need capnography to calculate the VDVT. So you take the arterial carbon dioxide, subtract the end-tidal carbon dioxide from that, and then whatever that number is, you divide it by the PaCO2. It's normally going to be a fraction. The normal VDVT is about 20 to 40%. It may go up to 40 to 60% on a ventilator because you do add a significant amount of dead space when you attach somebody to a ventilator. Normally, if this VDVT is very elevated, it indicates a significant amount of dead space. This could be both either anatomical dead space or it can be mechanical dead space. I should add that another concept called shunting, which is not dead space. It's a very different concept from dead space, and we've talked about shunting in our lectures, but I will not require you to use the shunt calculation for this exam, but you will have to know generally what normal values are for shunting if you run across those values. Generally, a shunting of approximately 20% or greater is significant, and you may need to consider aggressive actions to treat patients that have shunts significantly higher than 20%. In some cases, mechanical ventilation and the application of PEEP, positive index expiratory pressure, is required for significant shunting. Okay, moving on to the PF ratio. The PF ratio is the P little AO2 divided by the FiO2, and I can see here we have another wonderful failure to convert from the iPad to Keynote on my MacBook. Anyway, continuing on, PF ratio is the P little AO2 divided by the FiO2. The FiO2 must be converted to a fraction. Again, if I have 50% FiO2, I need to convert that to 0.5. The normal PF ratio is at least 2 to 300. That's normal. Low PF ratios indicate some sort of problem with the diffusion of oxygen across the alveolar capillary membrane. 2 to 300 is normal. 150 to 200 indicates the potential presence of an acute lung injury, or ALI, and a PF ratio that's really low, less than 150, indicates possibly the presence of acute respiratory distress syndrome. Now, if I have a very low PF ratio, certainly less than 150, my patient is probably not going to be a candidate for weaning. So that is something you want to be aware of. Okay, we have compliance. Lung compliance is in general defined by the change in volume, delta V, over the change in pressure. We have two types of compliance we can measure. In respiratory therapy, we have the static compliance, or the CL static, and the dynamic compliance, the CL dynamic. The static compliance is particularly important. And again, I can see just another mess up that has occurred here. I do apologize for that. But continuing on, the static compliance is calculated by taking the tidal volume in milliliters, and you divide that by the plateau pressure, the P plat, minus the PEEP. Okay, so you take the patient, whatever their tidal volume is, and you divide that by P plat minus PEEP. The normal static compliance is 50 to 100 milliliters per centimeter of water. Lower than that indicates low or poor lung compliance. You have very stiff lungs. and there are several things that can cause that, such as fibrosis, pneumonia, chest wall burns, abdominal compartment syndrome, and so on. The other type of compliance we can measure is the dynamic compliance, and it's very similar to the static. The only thing that changes is instead of P-plat, we use the PIP, the peak inspiratory pressure, minus the PEEP. So it's tidal volume divided by PIP minus PEEP. So don't let those two calculations confuse you. The static compliance is a tidal volume divided by P-plat minus PEEP, and the dynamic compliance is a tidal volume divided by the peak inspiratory pressure, the PIP minus the PEEP. Okay, here we go with airway resistance, or RAW. Airway resistance is calculated as taking the peak inspiratory pressure, the PIP, minus the P-plat, divided by the flow in liters per second. Okay, so generally the flow, it will be given to you in liters per minute. You will need to divide that by 60 to calculate your flow in liters per second. That's the big issue that we have when people attempt to calculate the airway resistance, is they forget to convert liters per minute into liters per second. So it's PIP minus P-plat divided by flow, or V dot, in liters per second. Normal raw is 1 to 2 centimeters of water per liter per second. However, this can be increased up to 2 times as much if a patient is on a ventilator, because the ventilator circuit, endotracheal tube, and so on tend to add a little resistance, or significant amount of resistance. So we know that elevated airway resistance is related to the presence of secretions, mucus plugs, bronchospasm, small tube, kink tube, some sort of obstructive pathology. And finally, we'll move on to the work of breathing calculation. Work of breathing is can be calculated in 1 of 2 ways. The first way involves calculus, and you actually have to integrate an area underneath the curve of the volume pressure loop, and you've got to find the function that works and find the antiderivatives and so on. And it's kind of complicated and not required for this course, so we'll use the approximation method, and that is take the patient's peak inspiratory pressure, subtract from that the P-plat multiplied by 0.5 divided by 100 times the tidal volume in liters. You need to convert the tidal volume into liters for this formula to work. Also remember your order of operations for mathematics. On the top, the numerator, take the plateau pressure, multiply it by 0.5 first. Do stuff inside of the parentheses first. Whatever that number is, then subtract it from the PIP. Whatever number you get after that is then divided by 100 times the tidal volume in liters. The normal work of breathing is about 0.5 joules, and we know that significantly elevated work of breathing indicates that the patient is having to work really hard to breathe. Another quick calculation you need to be familiar with is ideal body weight. Calculate it in the male, it's 106 plus 6 times the number of inches over 60. 60 inches is 5 foot, so if I have a 5 foot 2 inch male, the calculation would be 106 plus 6 times 2. Again, do the stuff inside of the parentheses and then add. So 6 times 2 would be 12, and then 106 plus 12, that would be your ideal body weight for a male who's 6'2". Female is 105 plus 5 times the number of inches over 60. Be aware that this calculation will calculate ideal body weight in pounds. If you are dealing with a calculation that requires kilograms, you will need to divide your answer by 2.2 to get to kilograms. And finally, the quick calculation for anatomical dead space is 1 milliliter per pound of ideal body weight. And in this course, with this exam, you will have to calculate alveolar tidal volume, and you will need to subtract anatomical dead space from the tidal volume to get at the alveolar tidal volume. Okay, guys, I think this concludes the review of the crucial formula for respiratory physics exam 2. As always, guys, have a great day, and thanks for hanging in there.